Can everybody hear me right in Korea? And can everybody also understand my quaint Dutch accent? Good enough? No worries there? Just a couple of quick questions in the beginning. So, who here is native English? Who is programming for a living? Ooh, that's good. Who's programming Scala for a living? Also very good. Who likes type level programming? Check. Okay. So, thanks for having me. It's nice to give a talk. I gave this talk at the Lambda Conf in Boulder this year also, so I hope nobody was there, and if you were, I hope you were not in my talk at that moment. What I want to do is some type level programming, but then some real type level programming. So if we think about programming, normally we are thinking about functions, operations, data, and data on, also operations on data. So there's actually something which we are telling the data to do. And every time that we're talking about type level programming, we do not directly have that type of possibilities. It's never that you go to type level programming and at the type level you are saying something like, this thing is a string plus a string, and you need to do that absolutely that it is 2 times a string, but only if this int value also contains something else. So we do not have real sort of tools to program at the type level. And since a lot of type level programming has a lot to do with recursion, or actually using type inference to let the compiler calculate through recursion a type, you can think of something which is called the fixed point combinator as something as an operation on types. Has anybody here ever heard about fixed point? That is a lot less. And I'm very happy because first I want to explain a little bit of fixed point at value level, and then we're going to lift it to type level. So let's go very quickly through the value level because it's quite late already. So let's say that we have, oh, and by the way, sorry that I do this directly from GitHub because some issues with the computers, but that's what always happens. So if we look at this function, I think most people know it, even though it is in Lambda representation. Does anybody have an idea what this function is? Factorial, obviously. So we have something which takes an integer. It will output an integer. We take the integer as a lambda, so not as a parameter. At the moment that the integer is 0, we directly return 1, and else we recursively multiply by calling ourselves. So for this it is necessary that you can call recursively. And as Scala programmers, also as Java programmers, we're pretty used to programming recursively. But just for the moment, let's imagine that it's not possible to program recursively. Then you could think of the function underneath as something which is almost factorial. And you can see it takes n, it has the whole structure of the factorial function. The only difference is, at the moment that it's going to recurse, we're not going to recurse with the f, but what we're actually going to do is then we are calling a higher order function. So if you look at the type of fuck-like, it takes first a function from int to int, which is going to be called at the moment that we recurse, and then it yields a function from int to int. If you, for the moment, already just assume that somewhere in a library there is such a function as a factorial, then it's pretty easy to see that, and this function was called factorial like, that if we have this library function which already calculates a factorial, it's pretty easy to see that the factorial like one time called also is factorial, because we put factorial lib over here as the first function, and thus it is called at the moment that it is recursing, and the rest was already factorial. So also factorial is factorial lib, if it would exist already, as the first function parameter to our factorial like function. And that means that we could also call ourselves, just like in the previous example, but that would mean recursion. And if we recurse, we need to implement it anyway as such a lambda, because otherwise it would always continue to evaluate, because Scala is a strict language, and at that moment it would blow up the stack. Small utility method, just identity. Identity is something which takes an A and will return exactly that same identity. In the first talk we saw the same with map values. Takes an A and it would directly return an A. It was not being used at all. So now let's assume that because we directly return A, we can make a factorial working up to the input number 0. And the reason is that if we go to factorial like 0 already works, we're never going to recurse at that moment. So now I have a factorial which works at the level of 0. And now conceptually you can think of that function, factorial up to 0, we can then put in a factorial up to 1. And now we have a factorial function which works for 0 as input and 1 as input. And we can continue that, and that way sort of build up a stack with never calling a recursion. And again, just to show, we can also do a factorial up to infinity, which means that because infinity, there's only one infinity, we go and we recurse to factorial up to infinity. But that would never terminate for exactly the same reason which I explained before. You always need to do it as a lambda. So what we learn from this is that a fixed point of a function, the easiest way, and I'm pretty sure that everybody already played with that, if you ever played with a calculator, think of it as repeatedly apply a function to a value up to the moment that that value doesn't change anymore. And that is the fixed point of that function. Think of a calculator, you type in a number, you press the cosinus sign, you press again the cosinus sign, and again, and again, and again, and again, and at some moment, if there is a fixed point, and cosinus has a fixed point, it will yield only one value. So that is what a fixed point of a function is. No questions, I think. So here we're going to derive a fixed combinator to see a little bit more what the fixed point combinator actually is. So if we define that if we give a function f to our combinator, that it will yield the fixed point of that combinator. And we also know that if we apply again f to the fixed point of f, that it will yield exactly the same fixed point of f. Then we have two equalities, and those two equalities, by equality and by substitution, we can work out. And there we get to the official definition of a fixed point of a function. Fixed point of a function is the function applied to the fixed point applied to the function. And this pattern, f fix f, that is what you need to remember. The thing which you are calculating for, you see as the first parameter, and you see it as the outside function which is being called. So let's say that we do that typed. In Scala, that is incredibly ugly. You would like to do this in a non-typed language, because in a non-typed language you could define it, for example, like that. But unfortunately in Scala, with all its type parameters, you need to be able to also make sure that the compiler is able to read those, is able to infer those types. And for that you get this horrible type signature, which I'm not directly going to explain. Other than that, I want that you should see a recursion in it. If you see here A goes to A, and here you see something goes to exactly that something, but that something itself is an A to an A. So there's sort of a deeply nested recursive structure here in this fixed point. And then over here, you see that the fixed point actually is precisely the same as the definition. At the moment that with lambda parameters this is being given in. And because we want it to terminate, we again have the final parameter A, which we then apply to this fixed point function. And this works. I'm not going too directly into it, but this works at type level. And at the type level you have never used it in your industry and never used it in practice. Sorry, not at the type level, at the value level. At the value level you have never used it in industry, because at value level this is actually only interesting for more or less theoretical purposes, in which you want to think quite deeply about it, what it means to recurse. And there's theoretical interest. So, if we have now factorial fixed, we can now, because we had this fact-like, and I will scroll up to show that fact-like was just sort of the skeleton of the, how is it called? The factorial function. It's the skeleton of the factorial function. But then that skeleton of a factorial function you can put into our just created fixed point, and that would give you a real factorial function. So you use the skeleton of a factorial function, you give it to the fixed point function, and instead of that it gives a value, at this moment it returns a function which calculates the fixed points. All of this is all at value level. Not interesting. But just as sort of a little bit of background. Now we're going to make it interesting. Now we're going to raise this fixed point to a type level, and we're going to use it as an operator at that type level. And I want to give the use case, the example, to build very quickly in just a couple of lines of code, something which is called a heterogeneous list. I don't know, has anybody ever used shapeless? Yeah, a lot. Yes. Now that's cool. We're going to create the basis of shapeless in just something like 8-9 lines of code. I want you to look at this case class. This case class is itself a type, and the type is fix. And it takes a type parameter, which we call f, but this is a specific type parameter. It is a type parameter of a higher kind. And a higher kind means, in our language, in functional programming language, we would call this type of f, kind of f, we would call star to star. And that means if I give it a concrete type, then it gives me back a concrete type. Can anybody give another example of a type which is of kind star to star? Where? List. True. List. List has one type parameter, so it is not a concrete type yet. You cannot use it at this moment. But in Scala we can say a list of string, which means I give it a string, and now list returns a list of strings. And if you look at how that is written, you can see already a little bit sort of a function. It takes an input type and it will compute a concrete type. Very good, cool. So here we have this case class fix, which will take a type parameter of a higher kind, and at the value level we will then make sure that when we instantiate it, that it has this pattern of the function, the fix, and the function, or I should do so. The function, the fix, and the function on front of it. It has exactly the same pattern as that it has at higher level, at value level. Let's build a little bit of a list, but let's do it in the like version. So we're not going to boringly create our own list. We're going to create a trait list which is like a list, which has a head and a tail as type parameter. And that's different than the normal list. Well, because the normal list only has one type parameter. So here we say that the head has a specific type, but we're saying nothing about the type of the tail. And the type of the tail is just another type parameter. It's generic for our list like. And then in lists we need two constructs. We need the nil, which is the terminating case, and we need the cons. And both I also do in this like pattern. So cons like again takes a head type parameter and a tail type parameter. It will maintain the head and it will maintain the tail, and it extends from list like and head like, and with that it is a data constructor for our list. It's cons like. It's not really cons, it's cons like. Exactly the same for nil like. For nil like we know it will never hold a value. So nil like can extend directly from list like. Doesn't have a head, doesn't have a tail. That's the nil. And I create quickly an object for it which extends, so that I don't, at type annotations, need to do this ugly name dot type instead of objects. With this as my abstract data tree for list like, we can now create the type of a real list of A by letting the compiler calculate this type by using the fix operator. So a type list of A will be calculated at compile time and will always be a fix of list like of the same A, and this question mark here, that is so that I don't need to annotate directly all the other types which are being calculated. It's called the kind projector, and a lot of type level programming sort of requires this as a plugin. It uses the plugin architecture of the Scala compiler to calculate those kinds. And then I can have two constructor functions. One is nil itself, and nil is nothing else than a list of A, because it's of the type list of A. And here I do exactly the same. I say fix the list like for the A, but give it this nil like operator as its original value. And with that I have a non-parameter function which I can use as the terminator situation for the nil. Exactly the same for the cons. Cons concatenates a head towards to a list. So I can define a function cons which will take a new head and an already existing list of our list type, and then I can fix the list like for that A, but now I can instantiate it our cons like out of the skeleton for lists. And with that, with just this thing, this skeleton to create lists at type level, and the actual definitions, we already have normal lists. So Here I cons a 1 to a 2 to a 3 to the nil. This is our nil, this is our cons, and the type of this here, if you see it in the compiler or at the moment that you make a mistake, will be quite horrible type of type signature, but I will show you later a little bit how you can go through it. This is not interesting because this is all already in the compiler. We know how this works. It's in the library, in the Scala library. We're going to change a little bit our fix because we have a little bit of small problem with our fix. Our fix case class holds a value which is of type f of fix of f. And that means that itself, it is not recursively computable at that moment for different type parameters, purely by limitation of the Scala compiler. If you would do this in Haskell, you would not have a problem. So I make a little bit of a change of our fix case class. Over here, remember that we had fix of f of fix of f, and the inner fix of f I take out as a recursive type parameter, which is bound by an inductive trait, which means that this part can only occur at this location for the co-product of that trait, and the co-product of that trait is very simple, an I nil, which terminates the calculation, and the I fix itself. So in structure it almost didn't change anything. The only thing that I really did was I took out the fix of f and I mapped it on a co-product with a trait. Co-products, is that name what I can use here? Everybody knows what a co-product is? Does anybody not know what a co-product is? Okay. A product is, think of a product as a tuple. Think of a co-product as something which can have or this or that type. So a sum type, basically also. Now I have my ifix, and with my ifix I can do exactly the same as I just did for the normal list, but at this moment for heterogeneous lists. So I create a type h-nil, which is the terminating case for a heterogeneous list. I just say that it is an ifix of a list-like. I reuse my list-like structure, and I give it the nil-like and the I-nil. And with that I have the type represented for a heterogeneous nil. And I also create a type which is a little bit of creation of syntactic sugar, which I like to be able to use later. I say the type of colon colon is something which on the left side of colon colon will contain the head, and on the right side is inductive tail. And this special feature of Scala, if you have a type which starts with a colon, it takes automatically the first type parameter on the left-hand side of that type, because that gives it a very nice structure in usage. Let me show that by skipping for the moment the h-nil constructor, but go directly for the h-cons. If you go to the h-cons, you see that what it returns is this a colon colon r. So it itself will return our definition of our type. And how do we compute it? Or not actually how do we compute it, but how does the Scala compiler during type inference compile this type? It will use our ifix for our list-like structure, the A as first, the recursive structure later, and we just give it cons-like. And in order for the compiler to calculate this, it is now going inductively through the tail until it ends with the ifix nil. And with that, it calculates actually a type with this ifix. Exactly the same for the h-nil. Ifix, list-like, nil-like, and I nil as the beginning. We give it the nil like with it. And with that, we added 4 lines of code to our ifix definition with reusing our list like ADT. And we are able to create H lists. For example, this H list will as first have an integer, the second will be a string, and after that it will terminate. So you have this syntax now to create them, and also because it integrates at type level, it also integrates with all the other types which we have. For example, if we have sequence of a list, which only takes one type parameter, type of A, we can now use our H list in exactly the same way. And that is actually pretty amazing, because I know only 2 programming languages which are able to do that. And if you know a third, I would like you to talk to me after this talk, which is now over in 2 minutes, so that we can drink beer. Because I like to know those type of